I was saying that direction of motion is elaborated here because we do not move the magnet, we move the coil, we rotate it. Okay, that's why direction of motion is there. Then the first finger gives us the motion field current. That means first finger giving us the direction of, or I'll use this symbol, direction of magnetic field. Lastly, the middle finger is giving us the direction of induced current or induced voltage or induced EMF. Alright, see, I have uniform magnetic field like this one. I'll be making 2-3 different examples, so it will be easier for you to understand the concept. What kind of magnetic field is this? Why I am representing it with cross? Because I am representing a uniform magnetic field, right, which is vertically inwards, normally inwards. If it has to be shown outwards, that it would have been dots here, right? First example is, I am not going to make any like straight good figures like a circle or a sphere or rectangular coil. Instead, I will be using very random different kind of shapes like this. In this figure, I have this shape which is going inwards. Okay, in this thing I have this kind of shape which is in that shape. In this diagram, the loop, whatsoever loop is this loop is coming inside the magnetic field. In this situation, the loop is going outside the magnetic field in this direction. Lastly, here I will be using a rectangular figure. For example, I am using a square and I am moving this square here to here to here and like this. I am rotating it in the magnetic field like this. This is the direction of rotation of the square. So let's find out the direction of induced current in each of the diagram. First of all, I have to use the right hand. Okay, so what is the rule? Motion field current. First of all, point towards magnetic field, not the motion. Set the motion later on. First magnetic field. My magnetic field is vertically inwards like this. Then motion is this side. That means the direction of flow of current is in this direction. What is this direction? This is clockwise direction. Point to be noted, some students are going to measure this or devise this formula on this side. Some students can do it on the other side. Problem is, if I'll do the same thing on this side, I'll get an opposite direction. So what should I follow? This part or this part? Always follow the part which is entering the magnetic field first. If the whole figure is entering magnetic field, that means if I write the name here, if it is A, B, C, D here, then when the figure, any closed loop, any form of closed loop, a rectangular, square, circular or the random shaped, when the closed loop is entering the magnetic field, you have to consider that part which is the first part to enter the magnetic field, and when it is leaving, then you have to consider which part? Not the last part, again the first part. Always again the first part which will be first going out of the magnetic field. So it is always the first part. You don't have to apply this formula right hand rule for the last part. Okay, just do it for the first part and your answer will be right. So coming back again, motion is in this direction. Motion field, first of all I will be setting field vertical inwards, then motion is towards this direction, that is what my thumb is doing, and the flow of current is in this direction. So this is how my current in this will flow, and this is an clockwise, sorry, it was anti-clockwise, right? Initially I said that is clockwise, right? It is anti-clockwise. Clockwise is this. In this case, again motion field current. Magnetic field is this side, vertical inwards. Motion is upwards, right? So the direction of flow of current is again this side, that is anti-clockwise. Motion field current. This is the flow of. Now, what should be the direction of induced current or induced voltage in this loop? let me name them A, B, C, D. This is A, B, C, D. First of all, guys, which part are you going to consider first? Will it be A, B or will it be C, D? The answer is, no matter what part you are going to take right now, as I first stated that you have to take the first part only, so the direction, according to direction of movement, CD is supposed to be the first part, but the answer in this case will be 0, there will be no induced current at all. Why? For the production of induced EMF, the most necessary condition is the flux has to be changing. When this loop was entering the magnetic field, there was an increase in number of magnetic lines of force passing through this loop or the closed loop, right? When this loop is exiting this magnetic field, there is a decrease in number of magnetic field of lines. That means again you have got what? The number of lines are changing, that is the point. But here number of lines passing through this loop is not changing, it is fixed because the loop is moving inside the magnetic field, inside the uniform magnetic field I should say. So that is why if suppose there are 10 number of lines passing through it, then no matter where you take it, there will be always 10 number of lines passing through it. So when you do that, phi 2 minus phi 1 upon time, phi 2 is same, phi 2 is same as phi 1, so it will be 0. So there will be no induced EMF and hence there will be no current. So do remember, keep this fact in mind that magnetic induction or the electromagnetic induction takes place only when number of magnetic lines of force either changes, actually it either increases or decreases, that means it has to change, alright.